hear me well? Okay, so first, thank you for giving me the opportunity to give these lectures. Second, as I arrived today after a short trip to another place, this week is Cultural Week in this campus. And I'm happy you chose this culture than the one outside. And I hope to give you a little bit of kind of AdS-CFT and holography culture during these lectures. So there will be 3 different topics, but all of them are connected. Initially, I told Ian and Suresh, these are 3 topics, which one do you want? And they both came to me and said, we want all 3. So I had to kind of compromise. So it's 1 lecture. So in the beginning, I wanted to give 3 lectures on 1 topic. So then you would have gotten kind of a full course on 1 topic. Now it's like going to this little places where in the market where you have different foods for different areas, and then you're gonna try it, and if you like it, then you can kind of get more into it. So feel free to ask me questions. So this is not actually, if you don't ask me any questions, if you don't like the course, we can finish quickly and then go and have fun outside. If you do like what you see, but you want to know more, just ask me questions and we'll use the boards. Okay? Good. Okay, so let's start from the beginning. So AdS-CFT. So the first few slides are going to be introduction, then we're going to go through these topics I'm going to introduce in a little bit more depth in later sections. So the rules of AdS-CFT computations at 3 level have been understood since the very early days of AdS-CFT. Basically, after maybe Maltasana static correspondence, we had the decoupling limit that motivated why gravity in AdS crosses 5 would be dual to CFT n equals force being Niels and a few other cases. And then a few months later, Gupser, Klebanov, Polyakov, and then Witten came up with some computational rules. Actually, the rules we're going to discuss are closer to W rather than GKP, although they're in the same equivalence class. So what are the rules? So the rule says that one is to compute the on-shell value of the action as a function of the fields which parameterize boundary conditions for bulk fields. And we'll discuss in slightly more detail later on what this means. Now, it turns out, if you actually try to do this computation, that the on-shell value diverges. And that makes sense because this is the bulk integral over a space-time, which is non-compact. So you do expect, because the volume of space-time is infinite, because the space-time is compact, you have infinities. And these are infrared infinities, because these are infinities that come from long distances. But quite remarkably, it turns out that these infrared divergences are local in boundary data, in what you specify here. This was a surprise. To some extent, now we understood it after 20 years or so. But to some extent, it's still a surprise, because if you move to more general theories of gravity, or perhaps more basically, if you just look at kind of Einstein gravity with no cosmological constant, this property doesn't hold. And precisely because this divergences are local, this means that one could kind of follow the ideas that was developed in quantum field theory the last kind of 70 years and set up a way to renormalize those in a consistent fashion. And this is called holographic renormalization. This is the Euclidean action, but there is also, you can also do it for Lorentzian. And actually, initially, when I sent them my preliminary program, I had 1 lecture on Lorentzian issues. We're not going to discuss today Lorentzian, but I'll be happy to discuss with you afterwards if you want to know a bit about Lorentzian. There are new issues, and there's new physics as well. So here, this lecture, all of it is going to be Euclidean. there's clearly enormous interest in Lorentzian. First of all, we live in a Kostas signature. Secondly, if one is interested to understand quantum field theory in generic states, you really need to work in Lorentzian signature. Or if you want to discuss, alpha equilibrium phenomena, then you need to work in Lorentzian signature. So you do need to understand these issues in more detail. There is a general framework to do real-time AdS-CFT computations. Okay. I will make this more precise because, again, this is the introductory part. I'm going to go through and discuss each of this. There's going to be 1 or 2 slides about each of this. So when I go there, if it's still not clear, then you ask me again. Okay, any other question? Okay. Okay, so again, precisely because it has a way to deal with these divergences. This means that one can develop well-defined rules that allow us to obtain normalized conformal field theory correlators. So since this very early days, this has been extended away from CFTs to general quantum field theories that you can obtain by deforming them one way or another. So all of this extends. So this is a general story. So in this lecture, what I would like to describe is a new work that aims to generalize these results to general loop order. So here, all of this was 3-level. And I would like to understand how to generalize that discussion to loop order. Now, this work, to a large extent, it could have been done 20 years ago, shortly after the things I just reviewed. One of the reasons that, at least back then, it was not clear to me whether that's kind of useful investment of time, was it looked incredibly difficult that you would ever be able to do a computation that would probe these results. But over the last 5 to 10 years, there has been a lot of interesting work in AdS-CFT correspondence where they do start computing loop corrections. And kind of the new tool that came into the town was this bootstrap approach to CFT, which allows to compute subleading corrections in the Toft coupling, which correspond to bulk loops. So now we reach the point where the CFT side is far more developed than the AdS side. And there has been kind of hand-wavy arguments about how the bulk would work, but there hasn't been a complete and systematic discussion. So the aim here is to present a systematic normalization procedure that deals both with UV issues. So while if you start including bulk loops, this means now you're going to have UV infinities in the bulk. But of course, you still have IR issues because the space-time continues to be infinite. And you have to deal both of them at the same time. And in pretty much none of the previous works, people kind of address both issues. And actually, as you will see later on, it is crucial that one deals with both issues. And the only reason this has been noticed was because people kind of knew what they wanted to get, and they would kind of fudge their way to see what they wanted to get. It was not, if you didn't know the results, you wouldn't have gone the route they went. So then what do you mean this Feynman? It will be Feynman graphs, but in AdS. We will, yes, we'll discuss Witten diagrams with loops. I will actually also, there were prescriptions in the past. In a sense, people would say, what sort of Feynman rules can I write down to write a loop? And they would do this, and they would get reasonable results. So what we would also do today is derive the rules that people use. It's not going to be an ad hoc prescription. It's going to be a first principle derivation. This is what you need to do, and that's how you get the relative factors that you get, and so on. Yeah, so this is the low energy limit of the genus expansion, and I will have a comment about string theory as we move on. Okay. So I think that's the discussion here is based mostly in this work with Max Bagnados, Nestor Bianchi, who is my student, and Ivan Munoz, who is Max's student, and he's looking for a postdoc position. So if people have postdoc positions, they should consider him. But I think it's more the beginning of the program. So it's not going to be. We are going to write a longer paper in the very near future, in the next month or two. It's ongoing, but it's going to be a lot more work. So this is just the beginning of the program rather than the end result. But I think the main ideas are now completely settled. Okay, so this was the introduction. So that's the plan now for the rest. So first I will go back to AdS-CFT 3 level, the things that were understood well 20 years ago, and I will discuss them in a little bit more detail. If you now have more questions about this, that's the time to really ask them. And then after we do this, and then I'm going to move on to put the setup, AdS-CFT at loop order. That will be the general setup. I don't think it's going to be something more general than what I will introduce here. And then I will implement it in the simplest case. And the simplest case is 5 to the 4th theory in fixed AdS background. And then we'll again go through all the steps. First, I will rederive 3-level results using this and also deriving the usual Witten diagrams that people compute. Then we'll move on to discuss loop diagrams for the same theory. And then we will see that so loop diagrams correspond to 1/n² corrections on the CFT side. And of course, we know from CFT that dimensions of operators receive corrections in perturbation theory. So we'll derive anomalous dimensions. But as you will see, and that's an important point from the theory of normalization, when you normalize, there is so-called scheme dependence, which I will define a little bit more carefully as we move on. And none of the previous work has taken into account scheme dependence. So at the face of it, what they wrote is ambiguous. And then we'll discuss how to obtain the normalized correlators, and then we'll finish with an outlook. Okay, so now before we delve into loop or start getting into more details, any general questions?
So before going to the details, is there some way to say generally what this regulator of the bulk loops would be?
Yeah, so we will have, we have devised a new regulator, and it is, roughly speaking, is geodesic point splitting. It hasn't been considered in the form I will discuss it in the past. But,
what if you do something like dimensional regularization in the bulk?
Well, the issue, you can do that perturbatively, and in some of my other papers, I'm using it. One of the issues is dimensional regularization in the bulk is not exactly the same thing as dimensional regularization in the boundary. So, and one has to be careful to separate the two. A second issue is there is an unfortunate feature of dimensional regularization, and that is that it regulates at the same time UV and IR divergences. And this can lead to mistakes because UV and IR divergences have different nature. You have to deal with them in different ways. So you have to separate. So for any theory, you first need to cancel. You have to regulate the IR, cancel the UV, and then check what happens to the IR. If the IR doesn't fix itself on its own, that's a sick theory. You throw it away. That's in a swampland of theories. If the right theories, then the IR divergences should cancel on their own. And that's, so there is, again, historically going back actually to the 70s, there are papers that they have mistakes because they were using the MREG, and then they were mixing UV and IR infinities. So we're using, this is UV candle terms to cancel things that look like UV, but it was IR, and then we'll get consistencies further down the line. So if you would use just DIMREG, you have to again separate the two issues carefully. And then the third reason is if you have fermions, which and supersymmetry, which of course generically we do have in these dualities, then DIMREG is not too happy with fermions or supersymmetry because this depends strongly in which dimension you are, especially if you have kind of chiral matter. But this is a regulator that everyone should have in his or in her pocket. It's the most useful and easy to use regulator, DIMREG. So tomorrow, when we'll discuss the CFT momentum space, we'll discuss everything's going to be done in using dimensional regularization. It is something one really has to know. Yes. Yes. Yeah, so when you do holography, you assume that the CFT is a strong coupling, and now I will be computing. So you take enlarge and limit. You are at strong coupling. I mean, I will review a little bit that in the next couple of slides. And then you're doing perturbative corrections in 1 over n squared. Okay. Yes. Yeah, so we're going to do 1 over n squared corrections. It's going to be, yeah, the loops means gravity loops or string loops or genus expansion, if I will have watch it, where the Toft coupling expansion, that corresponds to expansion in alpha prime string theory. So we're not going to be discussing alpha prime expansion. Okay, any other? Okay, so now let's start from the beginning, and let's start from the very beginning. So the correspondence is between string theory in AdS d+1 times compact space, which does play an important role for many aspects. And in a longer series of lectures, I would have discussed how to take care of that. But in this lecture, we're not going to discuss the compact space. And this theory here should be equivalent to a conformal field theory at the conformal boundary of AdS. So that's so this is again a correspondence that makes sense for all values of the coupling constants and at all energy scales. Okay, that's the starting point. This is the original conjecture in its strongest form. Now, of course, despite a lot of work over the last 20 years, we understand very little about how to exactly solve string theory in AdS, except in very special cases. So we're not going to discuss that. Yes, yeah. So usually you want to have, so that would be 9 minus d in some cases. So you go up to 10 dimensions. And in a few cases, you go up to 11 dimensions and have M theory. But when I discuss string theories, I should go to 10 dimensions. Yes. The boundary is going to be a CFT. Yeah, so I think all of this, so everything that we'll discuss today, I think have a direct generalization to all of these other cases. Non-conformal dualities, all of them. I think in a sense we're doing the simplest case in the simplest setup. That's why I said this is more a program rather than kind of a paper or two, because the framework is as general as it can be. And it's, I mean, still, of course, it would require some work, like, you know, from the beginning, from 97, 98, where AdS-CFT was first discussed, to start discussing circular normalization group flows, where you deform the CFT by a relevant operator that goes to quantum field theory and understand in detail how things are working. It took, I would say, maybe 4 years. I think from 2002 and on, we fully understand how to do these computations, but still took, even though conceptually it was more or less clear. I think similarly here, okay, after we settled completely all the issues in AdS, which hopefully will be done in the next year or 2 or 3, then one can start extending, go from CFT to quantum field, relativistic quantum field theory, which you can obtain by deforming it, or make it non-relativistic, and again go through the other steps. Yes. Say it again. On the CFT side, so far I'm considering the CFT on a non-compact space. Well, I'm considering the CFT on the conformal boundary of AdS. No, the CFT, in a sense, the CFT knows about the compact space. I mean, for instance, the fact that n equals 4 Young Mills is due to AdS5 versus 5. N equals 4 Young Mills knows about TS5. And more generally, one can understand exactly what the CFT has to do in order to encode the compact space. That could take us maybe, in one lecture I can give you the idea. To kind of start working in more detail, it would take maybe 2 lectures to give you a non-trivial example as well. But I would say that has been understood. This goes under the name Kaluza-Klein holography. Yeah. So let's now go to the second and then to the third. Now, so at low energies, this means we're only looking at roughly the lowest of the massless modes in of string theory. We get a supergravity on AdS, again times the compact manifold, which now the theory is a strongly coupled CFT. So going to low energies means I'm considering the theory a strong coupling. But this is still a 10-dimensional string theory. So that would be type, for instance, for AdS5 versus 5, it would be type to be supergravity on AdS5 versus 5. Now, once you have your theory and has a compact space, then you, without loss of generality, you can do a Kaluza-Klein reduction, not a consistent truncation. A Kaluza-Klein reduction, in the sense that Kaluza and Klein did it in the 20s, keeping all the modes, and then write that theory as a 5-dimensional theory coupled to infinite number of modes. So as long as you quantize this entire theory, you're losing no information. You're still 10 dimensions. So from here to there, I've done that step. So then from 10, I want to down to d+1 dimensions. And then this is still equivalent to the strongly coupled CFT at the conformal boundary of AdS. But now one of the differences between this and that is which of the fields am I actually keeping in the computations I'm going to do further down the line. That depends on which operators from the operator spectrum of the CFT I want to consider. So this does not change the theory. So the theory here and there is exactly the same. What you change is you're changing which part of the spectrum of the theory you're examining. It's like, I have a magnifying glass, and I can see everyone in this room, but I can choose to go and look here. The fact that I'm looking here doesn't mean that the room doesn't exist over there. So that step, that's the only thing that it does. It gives me a magnifying glass to look at a specific part of the theory in more detail. Okay. Yes. 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 Yeah, that's a good question. So there are 2 cases. So there are some cases where there is what is technically called a consistent truncation. So this means that for some computations, you can ignore all other modes. On the CFT side, this means that the dual operators to these fields close under OPE to leading order. Yes. What do I mean by reducing? I mean doing a Kaluza-Klein reduction. So Kaluza-Klein reduction means you expand all your fields. You expand all the fields in the harmonics of your manifolds. Then you insert this into the field equations. And then you diagonalize your equations according to the fields. And then you find new field equations from the D+1 dimensional perspective that give rise to the same equations. And then you integrate this back to an action. Okay, that gives you the lower dimensional action. Now, in much of the literature, people do something which is slightly simpler, but often is wrong. What they do is they do the harmonic expansion, as I explained a minute ago. They put it into the action, and then they integrate over the compact manifold, and they get a lower dimensional action. Okay, and then they say that's the action they use. Okay, in easy cases, in non-complicated cases, this is correct. Something which is slightly more complex is not going to give you the same answer. You have to do the first process. You put it in the field equations and so on. That's what I mean with that process. So there are cases. So usually the lowest mode is protected by symmetries. It's a singlet under a symmetry. And then that implies that this mode is okay. So in cases like this, then it's often enough to put in the action and reduce, because it's a symmetry that says that the process is going to be correct. As soon as you started reducing more modes, general is not going to be correct. I mean, it's still a consistent truncation. You have, I don't know, 5 fields. But the field equations are slightly different than what you see by reducing with the action. And the problem with this is there's no diagnostic. Now, once if you do the wrong procedure, you put in the action, you reduce, you get something, you find the field equations, all looks fine. You can get some answers and so on. You do not see something went wrong unless you do the right procedure, and then you see, oh, I didn't get the right action. Okay, so now we are assuming, in a sense, we've done this. So the context of, for instance, AdS-5 versus 5 would mean that now we have maximally supersymmetric 5-dimensional supergravity in 5 dimensions, and that has a solution, which is AdS-5. And if we just keep the supergravity, this means we're only dealing with supermultiple of the energy momentum tension. Okay, so now in this context, so once we're down here, I think this is the context where the dictionary is best understood. And it is the following, has the following 3 parts. So the first part is that for every gauge invariant operator of the dual CFT, there is a corresponding bulk field, phi I, in D+1 dimensions. And I guess this part here is what this was discussed in detail in Witten's original paper, and what convinced the majority of the community there's something non-trivial in this correspondence. Because n equals 4 per Young-Mills has a complicated spectrum of half BPS operators. And then the Kaluza-Klein spectrum of AdS crosses 5 has been worked earlier, and there is exactly one correspondence. And they were both of them knew before the correspondence, so there's no fudge factor into the game. The people knew the spectrum of n equals 4 per Young-Mills, also people knew the Kaluza-Klein spectrum of AdS-5 versus 5. And it's contains infinite number of fields, so it's very highly non-trivial that they do match each other. Okay, so now this is part 1. Now part 2 is now we're going to make a little bit more precise what we mean with boundary conditions. Now for each bulk field, there is a corresponding boundary value, which will be again make more precise in the next slide or two. And it's this guy here that specifies the boundary conditions for the bulk field, which acts as the source for the corresponding CFT operator. And then part 3, so here, in a sense, we kind of specify the kinematics. We say, in both cases, you have the same alphabet, or you have different alphabets, but we match them. So it makes sense that's the same theory, because it composes out of the same letters. So now next we need to do the dynamical matching, and the dynamics is given by that relation. So then this says that the partition function of the gravitational theory, this right-hand side, so this S here is the action of that theory down there. Now this is a path integral in a non-compact space, so this means to define it, you have to say how the fields behave at infinity. So then, when phi goes to infinity, this would be specified by that value. So when you do this computation, this path integral, the answer, whatever it is, it would be a functional of these boundary conditions. Right? You do an integral, and then it's going to depend on what you chose for this one. And now AdS-CFT says that now this object here has another meaning. It is the expectation value of Gauss invariant operators, where phi naught acts as a source for the dual operator. So the brackets here means that now you do the boundary path integral, where the action is the action of the CFT, of this strongly coupled CFT, and you do expectation values in that CFT, where you turn on the source for the operator O. And AdS-CFT says these two are the same. Yes. So far I haven't yet gone to 3 level. This is still all true, and we're gonna make this equation more precise when I go to my section 2. So I've now turned on the source. As long as I say I have bulk fields, I will actually let's wait for another slide to do, then ask again if it's not clear. All backfields that you have at that stage, yes. Okay, this is still a little bit hard to deal. So bulk 3 level now means a CFT in the n to infinity limit, where you keep fixed the Toft coupling fixed and large. So it's large because here we're considering gravity. And 3 level means that I take n to infinity. So now in this limit, where the coupling constant at the n is as large as it can be, then this path integral now can be evaluated with a saddle point approximation. And that's why we go now to 3 level. So now this, at the linear order, if I do saddle point, is just the on-shell value of the action, which again is going to be a function of phi naught. And now on the right-hand side, I have the generating functional of CFT connected graphs. So here, I take saddle point and I get a log. That's why you get just the on-shell value of the action. And then here, when I take a log, this means I keep the connected graphs. And that's where, in a sense, GKPW is. I mean, that's the statement kind of they made. Yes. You have some theory that you have to, in some cases, you can derive, or you can derive a conjecture about what duals are by taking limits, considering branes and limits. And then you know exactly what the CFT is. And then even with Calabi-Yauch, there are examples you can have. Like there is a famous example with a conifold In some cases, you're only going to get partial information about what CFT is. And then you can work from there. You can kind of start computing correlators or study the properties to understand exactly what the theory is. The bulk tree level is always defined the same way because the right-hand side is always well defined. I start with some gravity theory, and then tree level means what means tree level, yeah. And then this. The spectrum would be different, yes. The spectrum would be, yes. So if you have different CFTs, I have different spectrum of BPS operators. This means this compact space would be different, or this CFT would couple to different matter. Yes, that's you will see in a minute. I'm going to discuss that, yes. You mean that, right? That's what you meant. Yes, yes. Yeah, I will discuss it in a minute. Okay. Now, at the face of it, this is infinity equal to infinity. So I could have written anything there, which would still be correct, because the right-hand side diverges because of the usual short-distance singularities, and the left-hand side diverges because of the infinite volume of space-time, because the on-shell value of the action contains an integral over all space-time, so it's infinite. So I could have written here, S square equal to W. It would still be correct at this level of discussion. Yeah. Anyway. Now on the right-hand side, of course, we know how to deal with the issues because there is 70 years of renormalization theory and 3 Nobel prizes, so we know how to renormalize the right-hand side. So the next task is to understand how to renormalize the left-hand side. If this relation is to make sense, one has to renormalize the left-hand side. Yeah, that's where holographic normalization comes in. And that consists of the following 4 steps. So the first step is to compute the most general asymptotic solution of the bulk equations of motion. Now, the fact that this is possible is special to AdS and a cosmological constant. It's true both for negative and positive cosmological constant, but the answer is not fully known for other cases. One needs to make assumptions. So I was asked, I think I have yet another slide, whether this is finite. So in AdS, the point is that given phi naught, I can always solve the field equations for arbitrary phi naught. There are no restrictions. Okay, and that had to be the case. That had to be the case for this correspondence to make sense, because we know that in quantum field theory, the sources of coupled operators have to be unconstrained because we function and differentiate with respect to them. So if you have a constrained source, then function differentiation becomes a lot more tricky. Generally, we consider the sources as unconstrained. So for AdS-CFT to make sense, it better be the case that I can solve the field equations and impose boundary conditions such that phi naught is completely general and arbitrary, and that's true. Okay, so now we find the solutions, the general asymptotic solutions. And again, in the longer version of this course, I would have now done an example for you. You can look my review from 20 years ago. Yes. Yes. So here I make no assumption about fall-offs. So everything is derived by the field equations. I start from an action; it has field equations. And then it's the field equations that tells me what are the fall-offs. I just look for the general asymptotic solution and the field equations that meet unique answer to that question for general phi naughts with no restrictions. Where in asymptotically flat case, first you have to start defining what do you mean with asymptotically flat, which terms do you include, Are you going to impose any conditions on them? How far further down the line you go? None of them are. Yes. Here there's no conditions. The mass, yeah, I don't have the slides here again in the local version. You should invite me again. So here, for general boundary conditions, there's always a covariantly conserved energy momentum tensor, which is finite by construction. And then you can use that to define, first of all, to set up a covariant phase space with this general set of boundary conditions, show that that converges with no conditions. And then in the cases where asymptotic killing vectors, you can define conserved charges. Again, for first principles, I think for in all other cases where there is, if there's no cosmological constant, there are many prescriptions about what are the charges. The case of AdS is the only case where this is not a prescription. This is a mathematical theorem, kind of an extension of kind of Nether's theorem. And the only reason one can do it is because one has complete control about the behavior of the field at infinity. Or in other cases, one has to make assumptions how the field would behave, or find a reference space-time to subtract, to remove the infinite part, or find some other, there are a number of different prescriptions in the literature. Where in this case, everything is derived. This is the action. If you have asymptotic killing vectors, these are the symmetries. Then you can use Nether's theorem to derive the corresponding current. You can see this is properly conserved. Then you can show if there is a black hole, the first law of thermodynamics will automatically hold, and all of that. So it's a much more complete story. Okay, so now once we have this, then we put it into the action, and we regulate by cutting off the radial derivative for finite range. I will have a formula a little bit further down. I mean, yeah, I haven't shown you my, maybe I can write it here. So I will use this kind of, this coordinates for AdS. Z equal to 0 is the conformal boundary, and I will cut it off at some finite value. So now, so we regulated the IR infinities, then we evaluate the action. Now, once you evaluate the action, you have them as a series in the regulated epsilon, and then the next step is to find a set of covariant counterterms that remove this infinity. So that can be done also in a complete systematic way. There's no guesswork required here. What you do is you go back to the general solution. So this is an asymptotic series using a small parameter, and then you do a formal inversion of the series to find the boundary conditions as a function of the fields, regulated fields. You plug them in, and then you get the action. Delta is a conformal dimension. Yes, yeah, that step I haven't shown you. Yes. Well, you can see that you can derive the Brightman-Friedman bound using these ideas. I mean, they derived it by trying to have well-defined energy. But as I just described in the previous question, in this case, that's not an issue. If you set up the problem properly, you automatically have that. But you can see that if the mass is below the BF bound, then these general solutions develop an unwanted behavior. So suddenly the action would start to become complex because you have oscillating solutions. And you can derive that you need the BF bound. So in this case, it is not an input, it's an output of the process. Now, I mean, you can start with the cases where there are instabilities. as long as the fields that you have in your theory, the fields you kept corresponds to operators which are either relevant or marginal, then the whole thing goes through. If it corresponds to irrelevant, that's a slightly different story. There are complications on the CFT, and there are analogous complications on the AdS side. Yes. Yes. Yeah, you do the Pfefferman-Graham, and it is more general because when you write down the field equations, then the field equations become algebraic rather than differential. And then at every step, you can find a more general solution. Okay, so now I had the question, I forget from whom, what did I mean with local? And I think the answer comes here. So you can see here that all infinities are local in the boundary directions. So there are no kind of integrals. So all of these terms are just local. The infinities are localized at a specific point. Huh? Yeah, but this is the overall integral of the boundary. So non-local infinities will have a second integral. Yeah, so if you are in dimensions, in even dimensions, in even bounded dimensions, then when you do this, you find there is also an infinity which explicitly depends on epsilon, a logarithmic infinity, and its coefficient is the holographic analog of conformal anomaly. So that's the conformal anomaly, and that is present only. No, log epsilon. The epsilon is a constant, and A is a local function of curvature. So in 4 dimensions, so in D equals 2, A would be, well, actually would be C over 12 over R. That's how you can derive the center charge of the dual CFT. In D equals 4, A is something like proportional to this. R is the Ricci curvature of the boundary metric, and this is equal to let me write it this way. That's conformal anomaly, has an Euler part and a Wahl squared. Usually the coefficient of Wahl squared is called C, the coefficient of E is called A, and what you get from this computation is you get A equals C. Phi is the more general solution, and in this case I have both the phi and also the metric. I included the metric, so the most general solution of gravity coupled with scalar. The only restriction is that the mass of the scalar should be such that the dimension delta is below D. Otherwise, any potential is allowed. Yes, yeah, you asked the question. Yes, yes, exactly. It would have been, phi of x, phi y with some kernel integral over y. Yes. Yes. So phi. So I have a field phi depends on x and depends on z. So that actually I will have a formula later on for the asymptotic expansion of this. That maybe I can even write it now. It's d minus delta. Why not? This is the source. Then I have a few other terms, and then I have z to the delta. some cases I have a log. And this is the source, as you would see in a few slides. This is the expectation value, so this is source. This is the VAV, and this is also related to the anomaly. This is this. And then the phi that I have here is this whole phi with z equal to epsilon. Well, people do use this formulas. But I mean, sometimes people, when they try to do a normalization, they do not rewrite it in this fashion. That's also wrong. That breaks diffeomorphisms. I mean, for this, to some extent, when people are not doing it right, they don't have a good excuse because it's algorithmic. Sometimes people want to avoid some of the steps in the algorithm, and there are cases where avoiding the step is not going to give an error. Or if you're only interested in qualitative features, in many cases, actually I know examples, even qualitative features are coming wrong. But in many cases, it's not going to get wrong if you just get a rough picture and so on. If you really want to do it right, if you follow kind of these steps the way they're written here, it's guaranteed to get an answer. There's no. This is a case where it's like a homework. There is a solution, and all steps are well defined. You just have to be kind of a good student and do all the steps. Yes. I think whoever wrote that paper is wrong. There is a general proof that I don't. You have to tell me the paper, then I'll tell you. I mean, there is a general proof now that, again, in the longer version of what you're giving you the proof, there is a general proof that the infinities are always local. So we have to modify the bulk theory to be of a different type than the usual theories we're considering. They will have more fields here. It will be of similar type. I mean, all of them, they're going to contain this piece is universal. That's why I have included it. This piece is always universal because it's the anomaly. The other terms could change. The fact that they are local does not depend. Actually, you would see also when I go to the loops, these terms continue to be local. You see, so okay, gamma ij is the induced metric at the regulated surface. So it's G. So let's call this. Yeah, let's create some space. Yeah. Yes. So let's say this is the AdS metric, the one up there. So then gamma ij in these coordinates is Gij at x gamma epsilon. So that would be 1 over epsilon squared. And then if it is just exactly AdS, it would be dxi dxj. And now I have here, I take the square root of gamma. So that would be 1 over epsilon to the d, and that's the divergence. So once you write it with covariant counterterms, all the epsilons become implicit, except for the log. So when you do this step over here, then you're going to have an expansion in terms of the sources, phi naught, and you're going to have explicit epsilons. but all of these explicit epsilons can always be absorbed inside this field. And so that's a good check that you're doing your computation correctly. If this fails, this means you made a mistake. No, I'm not assuming, no. So this is only required for UV issues. It could turn out that given a source, okay, so if I go back, let's go back here. Okay, so here I tell you this is the behavior of the asymptotic solution. So this is given. And then the field equations do not determine that. This is undetermined. By asymptotics. But it turns out, so even though here I have the entire phi, that in principle includes this piece always drops out, so the infinities are also locally determined. And then the irregularity in the infinity, what it does is determines this one. Yes, you don't need this, yes. But we'll go back to the regulator because we will compute also correlation functions. The counterterms may not preserve SUSY. Yes. In this sense, it says universal counterterms. They were derived. So this remove infinities in all cases, supersymmetric or not. That's why they're not by themselves preserve SUSY. Okay. Okay. So now already from here one can get draw a couple of conclusions. So first of all, a trademark property of local quantum field theory is that the UV divergences are local. And then there is another general principle for holography, which I haven't told you so far, but you see it now, so-called UV-IR connection, that says that the UV properties of the boundary quantum field theory are linked to infrared properties of the bulk and vice versa. So in quantum field theory, if you do quantum field theory, you can establish Ward identities and anomalies by, in quantum field theory, you only use the UV properties of the theory to establish those. And similarly, if AdS-CFT was to be correct, then you should be able to establish the same Ward identities and the same anomalies by just doing a bulk computation. And that's exactly what happens here. By doing analyzing the asymptotics, you find exactly the right Ward identities and exactly the right anomalies. So this anomaly here is the correct anomaly for a two-dimensional CFT or the correct anomaly for n equals 4 yields. So more generally, this analysis provides structural evidence for the AdS-CFT correspondence. So at the very beginning, and at least for the next 10 years, sometimes even here today, people would say, oh, AdS-CFT, especially people from outside the field, only holds for supersymmetric theories. Supersymmetry is crucial for the correspondence. And of course, it is true that in the beginning, people found evidence for the correspondence by just looking at supersymmetric theories. But the fact that the bulk theory describes a local quantum field theory, it's already evident from what I told you here, because you wouldn't expect a generic theory to have a local property in its infinities. So the bulk has the analytic structure to be a d-dimensional quantum field theory. So I would say what we already discussed shows that the bulk is a local quantum field theory. And I can also turn the same argument around to also argue that the bulk is a string theory, kind of going quite a long way. We started saying AdS-CFT is a duality between string theory and AdS and a quantum field theory in d dimensions. So here we kind of gave evidence, actual evidence, that the bulk is a local quantum field theory. Now we'll give you structural evidence, well, I would sketch structural evidence that the bulk is also string theory. Now, if you have a quantum field theory, the infrared divergences must cancel on their own, as we discussed also earlier in response to Ian's question. But by the UV IR connection, this means that the bulk should be finite in the UV, not normalizable. So on the quantum field theory side, we do not have counter terms to remove infrared divergences. These have to cancel. If they don't cancel, the theory is sick. So similarly, the bulk should not be a normalizable theory of gravity. It should be a finite theory of gravity. And the only finite theories we know are string theories. Yes? Yes. 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 Well, there might be cases where, in a sense, you cannot do many tests. That's true. But if you were able to solve quantum field theory on strong coupling, yes, yes. Yeah, yeah. Well, I mean, that's in a sense, we know more generally that effective field theories are useful below a certain cutoff. And then you can view the AdS-CFT kind of literature as utilizing this effective field theory approach. If you're not interested in describing the short distance behavior of the ions and the electrons, well, I mean, the control is the energy scale of the problem, which is intrinsic to your system, because that's what distinguishes kind of gravity from string theory. I mean, gravity. Actually, also when I will discuss loops, I will treat it more as an effective field theory. There is an effective alpha prime. And if you go to energies comparable to alpha prime, then then you need string theory. As soon as you excite the first string nodes, you need string theory. So the previous slide was, so we arrived at the conclusion that the counter terms are local. Okay. Now in local quantum field theories have the property that their infinities are local. They have a generic quantum system, which is not a local quantum field theory, is not going to have these properties. You can, let's say, start with, I don't know, a spin system where you have correlations, not near neighbors, which are local, but to all orders. Then, and then you go to the continuum limit. The infinities are not going to have this property. It's a local quantum field theory. So here, we analyze the on-shell value of the action as a function of the sources, and we found that the infinities are local. So the on-shell value of the action has the analytic properties of a local quantum field theory. Yes. These have the same structure as the UV infinities of a quantum field theory. Not because of the CFT, because I just computed them. I haven't done all the details, but I mean, I just did it here, right? I said I have a gravity, I go through the steps, and I find the infinities, and then I observe these are local. It doesn't come from the CFT computation, it comes from gravity computation. This was the very first paper with Pennington in '98, where we set up this formalism to compute that guy over there. And it turned out the gravity computation gave exactly the same answer as the quantum field theory computation. I mean, this is all gravity, but nevertheless looks exactly like quantum field theory in a non-trivial fashion. Yes.
So suppose if I revert this logic, one way to test it would be that I take some effective filter in the month minus weak gravity component. I mean, as effective filter is fine, but will not be condition.
Well, I mean, at this point, I would say the better example, which is in a sense is still which a lot of progress over the last 10 years is more asymptotically flat gravity. If you try to do the same computation, at this stage you find no local infinities.
I'm not talking of this actually. The final.
So a final one. Okay.
Yeah. So if I do an effective filter in the bulk where you violate weak gravity conjecture, I can always take a massive field. Its mass is larger than or the charge is larger than the mass. So effective filtering where nothing is wrong, but we know that such a thing is unlikely to have a unique conclusion.
Yeah, I would say that's an interesting perspective, but I don't think it's related to what I say here.
No, but in the dual UFT, you should have some inferred problem.
So if the theory definitely has no UV completion, yes, that I agree. Then the dual theory should have problems in the AR.
So an interesting question could be like how to see that.
Yeah, but then we have to set up the holographic duality, and then try to understand. Yes.
Yeah, but now it's an infrared problem, which is
yes.
Instead of a UV problem in gravity, you get an infrared problem. That would be interesting to see that.
Yes, it would be interesting at least to try to have some putative dual and see that in a sense the UV looks okay. But now the problems with weak gravity conjecture should translate into some IR issues. Yes, that's an interesting perspective. Yes, I agree. Yes. No, the local bulk equations do not imply local infinities in the on-shell action. If you have a cosmological constant, then you would end up with a similar structure here. If you don't have a cosmological constant, you do not end up with such structure. Yes. Yes, there is. Yeah, so you can once you understand here, of course, I've done directly, and I will make it more precise as we move on. But once you understand directly, you can understand all other cases, because what it requires to go from one set of boundary conditions to different ones, let's say from Dirichlet to Neumann, it requires a finite term boundary term. So once you understand renormalization and all the issues, the rest do not interfere with the infinities. You can straightforwardly go to all other boundary conditions. Good. Okay, so bulk. Anyway. Okay, so bulk loops. This is the start of the discussion of bulk loops. So at low energies, again, the bulk is given by gravity coupled to matter. And now, of course, at low energies, this should be viewed as an effective field theory. And loop diagrams, of course, do have bulk UV divergences, and they must be normalized. But loop diagrams also have bulk IR divergences, and this would need to be dealt with holographic normalization, and there will be an interplay, as we will see. So before I move to bulk loops in AdS,
because I think we shouldn't hurry with this, so maybe we can.
Yeah, it is a good time to break. Okay, are we ready? Okay, so to recap, we discussed how to do tree level, and we can come back to tree level when we're going to discuss correlators in the example. But now we're gonna try to switch into loops. So in this slide, I argue that the bulk is a string theory, and string theory doesn't have UV infinities. Of course, from the low energy perspective, there are infinities because the bulk UV divergences view them as a quantum field theory on a fixed background. Okay, this do have infinities, and this need to be normalized. So let's first just quickly review how we deal with those in flat space. Yes. So I will discuss in more detail exactly with what you compute, but you should think of it as the bulk action is the action that defines the theory, and then I write down the Feynman diagrams from that action, and then write loops, and these are the loops we're computing. But all of this I will try to make precise in the next section exactly what we meant to compute. Okay, so now gravity coupled to matter in flat space is of course not non-normalizable. That's the main problem with quantizing gravity. And cancelling infinities requires introducing high derivative terms. In principle, you can just skip what you're doing in quantum field theory. So you find an infinity, you know the infinity would be local, just on the property because you started from a local quantum field theory. So this means there would be a local term you can add to your action to cancel that infinity. But in general, it's not going to be the same action you started from. You need to add a new term. So that could be a high derivative terms, because the more loops, the higher the degree of divergence. This means that you need more powers of momenta to cancel. That's why you have high derivative terms. Now, in principle, you can do that order by order, and some people do that. But now, for each subtraction, there is a finite ambiguity, because infinity plus finite is also infinite. So when you do the subtraction, you can always, at the same time, add a finite constant. And this is called scheme dependence, because it depends exactly how you do the subtraction. So that's the reason that the theory now depends on infinite number of, so the theory depends on infinite number of high derivative terms, each with its own undetermined coefficient. So we need an infinite number of coefficients to fix. That's why the theory is non-normalizable. Now, when you have scheme dependence, not just in gravity or in ordinary quantum field theory, you always need renormalization conditions to fix. You need to say, you give some physical conditions. Like, for instance, you can say, my theory has a particle of that mass. Or you can say, if I compute the 4-point scattering, then that will be the answer. And then I arbitrate external x, that's the answer. And in normalizable theories, you need a finite number of renormalization conditions. And then this fixes the arbitrary constants, this is scheme dependence. And then any other observable is now completely fixed. And you can go compare with experiment or make predictions. Now, if you do gravity with no other input, okay, that would require infinite number of measurements, and then the theory is not predictive. Now, when you do have a UV completion that you know, like for instance string theory, then it's string theory that provides this infinite number of constants. So the way you fix them is you compute the same amplitude in string theory. Let's say you have a 4-point or a 5-point amplitude. Then by construction, string theory is UV finite. So this means the answer has no ambiguity. It's going to be some function of momenta that also depends on alpha prime. Then you take the low energy limit. And then in the low energy limit, the string theory amplitude, it would reduce to the field theory amplitudes plus amplitudes for high derivative terms, but with very specific coefficients that all come from the specific UV completion. And then that's exactly how you fix this undetermined coefficient. So now you do one computation string theory, gives you all of this infinite number of coefficients, and then you fix them, then you have a predictive framework. So for example, a famous example is this after the 4 correction, which is the linear correction, low energy correction in type 2B string theory, where it comes with a very specific coefficient, which is kind of 1, and it has a 3-level, 1 loop and non-perturbative terms. So this is what we do in flat space. And as you would see, the story is analogous with, because you have a known function, depends on alpha prime, it depends on one parameter, and then you expand that function in alpha prime. So now what happens is, if you want to see it in detail, what happens is you find terms that contains poles. This is when physical particles propagate. And then the rest have a regular expansion alpha prime, and this gives the coefficients of the high derivative terms. It does depend, because the actual string theory computation, the string theory amplitude depends on all details of your string theory. It's 10 dimensions, flat space, 10 dimensions. It's 4 graviton scattering in flat space. Somebody else said yes. In general? Huh? In general dimensions, yes. Well, so you mean for the R to the 4? So the R to the 4 is known in 10 dimensions. And then in 10 dimensions, there are other terms that appear at the same order in derivative. These are not known, even after 40 years of string theory. Now, to really get them in 4 dimensions reliably, you need to know all hard derivative terms in hard dimensions, because once you combustify, things start mixing up. But in principle, as a matter of principle, with enough, suppose all of you guys tomorrow decided this is the problem we want to solve, then we just need to, we need to compute up to 16-point amplitudes in flat space in type 2B, and then we get all. Then you need to get the integrals over moduli spaces and so on. These are finite integrals. So in principle, we have supercomputers. So you can put them on Monte Carlo to evaluate the integrals. So now we can do a kind of a project with get maybe a record for the number of authors, and then compute all of this, all terms, and then go back and find all coefficients in 10 dimensions. And then we decide what is our favorite combustification, and then combustify that, and then get exactly all the numbers. People do compare, but all of this, I would say, are tentative, because there are clearly other terms that could contribute. People close their eyes and they compare, and sometimes it agrees, which suggests the terms you don't know that do not contribute. And sometimes maybe people get different answers and they try to cook up some physics reason. Yeah. Yes. He has not managed to compute. I think probably the closest, I tried to do them in 10-dimensional superspace 20 years ago. And I was very close to get them, but there's something missing there as well. But, yes. All of them. I tried to do them in superspace in 10 dimensions. I had to, anyway, that's another talk. This was very, very close to work. Actually, all the known terms come from the same. It's clear that the answer that we gave is not completely correct. That's definitely the case. But some of the terms, people extracted some of the terms we gave, like the terms with the 5 form. Actually, before our work, everybody, all the experts were saying it's not possible 5 form corrections to that order because of the self-duality. And okay, that turned out not to be correct. So there is a specific term, and then you can fix its coefficient by comparing the branes and black hole entropy, and all seems to work, but there's no complete answer and first principles derivation. Okay, so now what we will see in the AdS context, we'll build instead the analog of that. Okay, we'll see that one can make it completely analogous to this. Okay, so now we're going to move to what was meant to be the topic of today's lecture after this little introduction. So the first part is, now we'll try to set it up completely generally in a way that it would apply to all cases. And in enough generality that, again, one would be able to capture all cases one is interested in. And then we're going to go on and discuss the steps in the specific example, the simplest possible example. Okay, so let's first start, what is the statement of the duality? Now I'm restating again what I stated at the beginning, but now it's going to be a little bit more general. So this is the statement of the duality to all orders. So now let me unpack it. So phi naught, as in the as earlier, denotes collectively all boundary conditions and sources. So appears on left and right hand side. Now the theory on the bulk, it could depend on a number of parameters, like what masses you have, what constants you have, all of those. And this I will call collectively phi naught, P for parameters, and not because this is a bare quantity, it would be normalized and the naught would be removed. And I is because this is collectively all possible parameters. And then on the right hand side, I have an expectation value of operators in a CFT. So the CFT also depends on CFT data. And the CFT data are the spectrum of the CFT, what type of operators we have, plus in addition all the OPE coefficients. So if you give these pieces of data, if it is a consistent CFT, that uniquely specifies the CFT. So the answer on the right hand side would depend on those. And now we want to understand how to renormalize. Now to renormalize, step 0 is always to be very explicit about the regulators. The theory needs both a UV and an IR regulator. So we first need to introduce UV and IR regulators. So we're going to call tau the UV and epsilon the IR, and I will define them in the next slide. Then next, we introduce Z factors. So we take all the parameters that we have on our left-hand side. So here we do an operation on the left-hand side, right? And on the right-hand side is meant to be standard quantum field theory. So we meant to understand how to renormalize the right-hand side. So all the discussion would be on the left-hand side. So the left-hand side depends on phi naught and p naught. So we need to introduce a Z factor. So I say that phi naught is Z times phi, and then all the parameters are Z times pi. And then the bulk theory is normalizable if we can find such Z factors, and in addition, a boundary counter term action as counter term. So here at 3 level, you see we found a counter term action. It was 3 levels, so no need for UV infinity. So the only thing we needed was just this. But now we want to deal with infinities, bulk infinities. So we need to normalize, we need to be able to find Z factors and a counter action such that if I evaluate the bulk action in the presence of regulators and use these relations, then the limit epsilon goes to 0, tau goes to 0 exists. And then the answer should depend on now this normalized couplings, the ones that appear here. And in general, it's going to depend on a set of parameters Sj, which is this scheme dependence. So renormalized correlators can now be obtained by functionally differentiating with respect to these renormalized sources. This would automatically be finite because I cancel all infinities. The order of the limit might be important, one has to be careful. So the way, we would do it is we would fix the IR cutoff at the UV counter terms, then adjust the boundary action, and then show that you can remove the limit. So SJ here stands for the scheme dependence that you find when you adjust the z's to remove the infinities. And you will see it explicit in the example. There is a scheme dependence. Every subtraction that you do, it has a finite dependence. So the left-hand side would depend on the normalized sources, but would also depend on the SJs, this scheme-dependent functions. And then, in order to fully fix our theory, we need to supply normalization conditions to fix these CJs. So this is the general prescription. Okay. Yes, yes. Yeah, so that's this is the object of interest. So we always stay on the gravity side. So from now on until the end of the talk, we're not going to discuss CFT anymore. So what I want to make well defined is the left-hand side, this equation over here. So that on its own, this is infinity equal to infinity. So now I want to have something which is finite on the left-hand side. And the way to do this is I scale my fields and the parameters, and I introduce a boundary action. This is yes. Now this object here should be equal to the normalized correlators on the CFT side. Well, the SJs, no, I mean they disappear. It's not just those. Of course, the multi-trays do develop anomalous dimensions, and part of the data would be what is the actual spectrum of the CFT, and this will be part of the way that we fix these parameters. Yes. Okay, so that's a central slide. So, any more questions on the slide? Okay. Yes. I will, now I'm going to unpack it further, tell you what are the regulators and so on. Okay, here, the regulators. Well, the infrared regulator is the one we discussed earlier at 3 levels. So this is the metric in AdS, and I'm cut off the result in this fashion. So now about the UV regulator. So first, what type of regulators would we expect? So we know that on the CFT side, infrared effects do not break any further the conformal symmetries. So the breaking conformal symmetries happens in the UV, not in the IR. So this means that there must exist AdS invariant UV regulators. And here is what it is. So let's consider 2 points in AdS, x and y. Then there is an AdS invariant distance given by that expression. So AdS invariant means that this expression here is invariant if I do an AdS isometry. So the AdS isometries are, you can do translations along the boundary directions, and you can see this depends on the difference. You can do Lorentz transformations along the AdS directions, and this involves a square, a Lorentz, this is a scalar product. You can rescale all coordinates, and then if I rescale both the radial and the radial direction and the boundary direction, this is also invariant. They're both scaled as a square. And then there's a slightly longer computation to show that this is also invariant if you do a spatial conformal transformation, or if you do inversions. Another way to see spatial conformal transformations is to note that this is translations followed by inversions. It's easy to check that this is inversion. Now, UV infinities come from coincident points. Short distances are the same thing as UV. And so if I put here Z1 equal to Z2 and X1 equal to X2, this goes to 0. Okay, so now I'll tell you how we regulate those. Yeah, maybe I can from this side. So if I have 2 points x1 and x2, what do they call them? What do they call them? X and y? Yeah. So what we do is, so in general, there are, if I have one point, there are infinite number of geodesics that live from that point, because then depends on the angle where I shoot the geodesic. So, and I'm going to select a very special one. So I look at geodesics, which I shoot orthogonally to the special part. So x and y are the boundary directions, and I shoot the geodesic just perpendicular to these points. And I go up to distance tau, so that would be, geodesic like this. So here, if this is x1, I would call this x1 of tau. And one can work out what these are. These are given over here, how the radial direction and the spatial directions change. And then one can show that if you do the computation, then now the distance, this distance here, this is between this point and that point, is related to the original distance in a simple way. So the u is the u of the displaced x1, x2 is given as a function of the original u. Now this u was invariant under AdS scalings, which means that one would be invariant under AdS scalings. So this distance here is also AdS invariant. And furthermore has the property that this becomes 0 if and only if the 2 points are on top of each other and tau is equal to 0. So as long as I keep tau non-equal to 0, this distance never becomes equal to 0, which means I have cut it off the short distance singularities in a way which is AdS invariant. This formula is exact. It's exact formula. No limit. No limit. Yes. Okay. So now, how are we gonna explicitly use this? Now, if you work out the propagator and the bulk, the so-called bulk-to-bulk propagator, this is given in the in terms of the so-called chordal distance, which is 1 over 1 plus u. And now again, a short computation shows that this regulated chordal distance is just a rescaling of the original chordal distance. So again, one can explicitly see this is AdS invariant regulator. So then the regulated bulk-to-bulk propagator is obtained by just replacing the chordal distance by the regulated chordal distance. And actually, this regulator has already appeared in 2018 in that paper. In that paper, they just did it in a sort of ad hoc fashion. They say, just rescale psi by some factor, and then use that factor as a regulator. But here we understand exactly what it means. We just do a kind of point split, geodesic point splitting. And then further analysis using some of the stuff you will see in the next few slides shows it disappears. Yes, exactly. And this type of regulator is enough to regulate or u infinity. So as long as you regulate the propagator, that's all good. Okay. Okay, so now let's go back to generalities. Now that we have at our disposal this regulated version, we can address some conceptual issues. So we know that conformal invariance fixes 2 and 3 point functions up to constants, and high point functions up to functions of cross ratios. Actually, tomorrow I will give you all the formulas exactly. I will derive those. So this means, so here I did not use any specific CFT. I didn't say this holds in any Kostas-Skenderis or it holds in Ising model or in any other CFT, free scalar or free body. It was a completely general statement. It was independent of the model. So this means that in the bulk, we should be able to establish exactly the same properties to all orders in the bulk loops without doing any computation. Like in the CFT, in any Kostas-Skenderis, we don't need to do, compute explicitly 5 loops to know that the 2-point function of gauge invariant operators will take the standard form. That's automatic. That just follows from conformal invariance. So similarly here, up to the kind of this work, it says this was done using a model. You have a scalar field, you compute at 3 level. I mean, that's what Witten did back in '98. Then you find that the 2-point function has exactly the right form to be a CFT 2-point function. But it didn't have to be that. It should have been this way, because that's a property of the invariance. It's not the property of the model. Of course, any given model within the class, you should reproduce that. But you should be able to give a general proof that does not rely on which model you're using. And this is indeed the case. One can do this. One can establish that 2- and 3-point functions and high-point functions take the right form without having to actually compute them. Now in CFT, also conformal correlators often need to be renormalized, and again we'll discuss tomorrow in which cases we need to renormalize and how to normalize them. And in particular, conformal dimensions also sometimes normalize. And in the CFT, that happens because of UV issues. You have UV infinities, and then you remove those, and that induces an anomalous dimension. So this means that in AdS-CFT, that should come from infrared divergences. 6, 7 infinite loops. Yeah, so you should be able to show this without having to compute them. I'll show you in a minute a general proof. Yes, I will sketch it rather than showing it. Yeah. Okay, so that's the generalities. Next, we're going to move to discuss now what I discussed in general, to how to apply them in an explicit example. Okay, any questions more on the generalities? Okay, so what's the model? The model is 5 to the 4 and a fixed AdS by count. So this is my action. So in this context, the pi naught I parameters are the mass and the phi to the naught. So now to discuss loops, we're going to take the bulk scalar field and we'll write it as a background plus a fluctuation. And the background field would satisfy the classical equations that follow from this action with Dirichlet boundary conditions. And Dirichlet boundary conditions, as I discussed there, means that this phi here, as you go to infinity, should go to a fixed value phi naught. This is something that we supply externally. So this is the parameter phi naught I had in my earlier slides. And then doing this perturbatively means that we need to integrate the fluctuations order by order in perturbation theory. So now my regulated theory is I reduce epsilon by cutting off this integration, tau by, as you would see in the next slide, in the next few slides, by doing this geodesic point splitting. And now my task is to compute this regulated expression and then find the right counter terms to make it finite. So this expression here has 2 parts. Has kind of a 3-level part, which captures the 3-level diagrams. This is the part we have been discussing earlier. So this 3-level part contains the regulated on-shell action and the counter terms we discussed earlier. And then there is the part that we get by doing the path integral over the fluctuations. So first, I'm going to focus back into three-level diagrams and discuss how this part gives rise to Witten diagrams. Okay, three-level diagrams. Okay, so for holographic renormalization that we reviewed earlier, it follows what I give over here. So if you vary this subtracted action with respect to phi naught, and then remove the regulator, then the answer is finite. And the answer is given by this formula over here, where phi delta is the term that appears in this order, z to the delta. So now if you want to compute endpoint functions, what you need to do is you need to solve the classical field equations to n minus 1, or you need to solve the field equations here, and then differentiate this piece here, n minus 1 times with respect to phi naught. Okay, this is going to give the correlator. Because in getting into this formula, we did one differentiation. So if you want an endpoint function, this means we need another n minus 1 derivatives, and then the derivatives would act directly on that guy over there. Okay? All good? Or are we getting tired? It's exactly, yes, there is an analog. Yeah, it is in same papers back from beginning of 2000s. Yes, you do not break edge variables. Yeah, there is an analog of this formulas. Yeah, there is an analog of those for any possible field. Yes. Yes. There's no restriction of what field to consider. It's not special to scalar. Okay, so now let's do that computation. Okay, so to do the computation, we want to solve perturbatively the field equation, treating the quadricoupling as a small parameter. So now the classical field would be now written as a series of terms where the index indicates the order in that parameter. So to linear order, the right-hand side is 0, so we just need to solve this equation. And this equation is basically the solution is given by a bulk to boundary integral. So here my notation, I use a kind of shortcut notation to avoid writing all the time integration. So you take phi naught, you act with the bulk to boundary propagator, and then this gives you the solution to this equation. And now if you want to do it to the first order, and then you need to include this term on the right-hand side, you substitute the 0th order solution, and then you integrate this equation. Now to do this, we solve this using a Green's function. So we need the Green's function of that operator, and that's the bulk-to-bulk propagator. So then the answer is the convolution of the bulk-to-bulk propagator with the term on the right-hand side. So now to this order, we know the bulk solution of this equation. And to extract the correlator, we need to pick out this piece here. So we need to understand how the solution, or what is the asymptotic form of the solutions. And for that, one needs to know the asymptotic behavior of the bulk-to-bulk propagator, which turns out to relate that to the bulk-to-boundary propagator. So now if we put everything together, that's what we get. So you can see from here, so each phi naught contain one bulk-to-boundary propagator, and there are 3 of them. And then G, in the asymptotic expansion, contains exactly the right power in the asymptotic solution, z to the delta. So then the coefficient of it is also k. So that altogether we get the usual formula for the so-called contact diagram, where you have, so this is here, this represents AdS, the circle is the boundary of AdS. I inserted an operator at each of the 4 points. I differentiate 4 times with respect to phi naught. And associated to each differentiation is a bulk to boundary propagator that comes from here, goes to a point in AdS, and then we integrate over this point. And this is the 4-point function. Yes, now that's it. So here I should have had only one delta, because I only consider one scalar field, and then the mass corresponds to one delta. But the same computation can be done for different scalar fields. It gives the same answer with different deltas. And I just did this because later on we're going to have also different deltas. No, so this is a very central function in AdS-CFT, has very interesting properties. Actually, one can actually do this integral exactly. It's given in terms of one of the hypergeometric functions, the Apple F4 hypergeometric function. That function would also appear tomorrow in CFT in momentum space. But this function also appear later on when we do loops. Okay, so that finishes my lightning review of Witten diagrams in 3 level. Any questions on those? So usually people, in most papers, people skip this in the slide, and then they write this. Yeah. But yes, it's a 5 to the 4. So if I will have 5 cubed, I will also have exchange diagram, and you will see that tomorrow. I will have this. But that's just, this is only 5 to the 4. I mean, that's in a sense a first principle derivation of that diagram. And the 3 level, there's little ambiguity that this was the correct expression. When you go to loops, the relative factors and so on, there was more ad hoc choices. Well, now we will derive all the factors and the expressions and so on. Okay, so now next we're going to do loops. Okay, so let's remind ourselves where we are. So we started from this action. We chose boundary conditions. We just discussed this. We computed that. Now we need to compute this expression here. So this expression here, so what we need to do is we need to we substitute phi in here. The pieces that only depend on this little phi are all here. And we need to keep all terms that depend on h. And these are given over here. So this S of h is the same action with capital phi replaced by h. And then we have a few other terms that come because the action was nonlinear. So then it will be when you expand the phi, when you expand this, okay, clearly this pieces, this was n subtracted, this is part of this, and then you also have a linear piece, which is that one. And because I will need to renormalize, then I have already substituted my z factors here. So here, so m naught, which is the original mass, was replaced by m squared plus delta m squared. It's quite often useful also in quantum field theory instead of having it multiplicative to have it additively. So I've done it additively. So this delta m is because of that. And then similarly for lambda naught, I wrote it as lambda, which would be finite, plus delta lambda, which would contain Cantor terms. So now we need to do this path integral. Wave function, you would see we don't need. We do need to normalize the source, but not the field. So instead, no, I think to all orders we just need to normalize the source, not the. So the analog of the wave function normalization is the normalization of the source. Okay, now the next step is an exercise in path integrals. So it's useful to introduce a source that couples with the quantum field. And then you can use this to now integrate, because this action here is quadratic in H, so this is a Gaussian integral. And so then you can integrate H to get in terms of J, and this is the answer. So now the important part here is that when you integrate out H, you get the Green's function of the quantum field, which is, and now we introduce the regulator. It is at this stage what we introduce the regulator. So this, which would be the usual Green's function, I now replace it by the regulated propagator, and all integrals here are contain the IR regulator. Yeah, that's this. It's not quadratic, yes. So here, this takes care of the quadratic, and then the other ones are, yes, derivative with respect to the J. So then what one needs to do is, if you want to work out specific correlators, you work out the derivatives to sufficiently order, and then you keep the terms that you need to that order, and then you do this computation, and then you set the J equal to 0. So for the diagrams we computed, so we did the computation to second order lambda, and to this order, okay, that's the answer that one gets. So now I want to connect the graphs. So I took the log. So then I will have the subtracted action, what appeared also at tree level, and then I will have here all of these terms that contribute to the correlators. And here I have already indicated that the action is definitely UV divergent, because I have, so I introduced this, so you recall the G depends on psi, and psi was 1 plus 1 plus u. The coincident limit, so u of x comma x with 0, which means psi 1, so psi equals 1 is the coincident limit. So this means this term without the regulator, this will be infinite, right? You consider infinities. Yes, yes, yes. So psi, so indeed, so psi tau with psi defined by cosine tau. So now if I go to the coincident limit, that becomes 1 over cos tau. So now, and in this expression, this small phi is the classical field we worked out earlier. So it's this phi 0 plus phi 1. So there's also a hidden lambda dependence. So if you want to have explicit all the lambda dependence, okay, you have to do this and put it in the other formula, and that's the final formula. Okay, so now we have everything we need to do the computation. And these are the diagrams to order lambda squared. So the notation is, again, the blue circle is the boundary of AdS, and we computed the corrections to the 2-point function and the 4-point function. And by just following, starting from here, you get all the combinatorics and so on. So that provides first principles derivation of these diagrams. You would have written each individual one with using Witten diagram rules. Yes, all the loops, all these loops are the G tau loops. Yes, yes, yes. So at this point, gravity is fixed, so I don't have any graviton propagators. Yes. This space position space, yes, yes, yes. So that's the diagrams one is to compute. Well, I think the three-level discussion I discussed a few slides ago, okay, that's in my review from 2002. For loops, people said, okay, let's use the same combinatorial factors as in flat space. It's correct. It works. And I can see why they would say this. I mean, I can see in the sense the heuristic behind it. It is now, we derived it, right? Now it is true. There's no question, yes. So now one needs to compute these diagrams. Yeah, that's the heuristic. The heuristic would be that the combinatoric should not depend on the background. Therefore, should be the same. I don't necessarily disagree that you know, I also do not. It was correct. There's no mistake in any of the previous literature, and I can see the argument. But I mean that's a derivation now. Okay, so yeah. For whatever is worth, it's yeah. Yes. Yes. Okay, so now computing the diagrams. That's a new Herculean effort, which I'm not gonna give you all the details, but I'm gonna sketch some of that because with what I told you so far, you can easily see, well, you can see that this would normalize all of these correlators. To actually compute them, you need to compute new integrals, and we also done that. That's why we have full answer for the normalized correlator. We have not only checked that this is normalizable, we computed the normalized correlators. And for that, in a sense, you need to deal both with EUV and IR issues. So let's now, before we go to the normalized correlators, let's discuss anomalous dimensions. And I will start by giving you an argument which is not correct, because pretty much, anyway, let's see what it is. So that I want to compute that diagram. That diagram has been computed in many previous papers. We're not the first one to do it. But the argument I'm going to give you, it hasn't been given in previous papers. So the diagram here, okay, that would be one back-to-boundary propagator, that's K. That's another back-to-boundary propagator, that's that1. And then we have this loop, which closes to itself. It's a tadpole. So this is this diagram here. You remember from here, psi of tau, it's psi divided by cos tau. Coincident limit means psi equal to 1. So this is a function of cos tau. So now this expression here, I can expand this for small tau to see the divergence. It goes like 1 over tau to d minus 1. So indeed, it diverges as tau goes to 0. And now if you start from here, you can now do conformal transform. You can do change of variables in x1 that amounts to conformal transformations of the boundary. So first, I can shift the spatial part of the integration by y1. So when I do this, this propagator here is not going to contain y1, and here we'll get y1 minus y2. And then I can do and then I can do a rescaling of the integration variable. And when I do the rescaling, this brings this difference outside this integral. And then what is left is an expression, which is the integral over x1 that doesn't depend on any parameter. So it's just a number. So after that step, so if I do exactly this change of variables, we see that the answer for that integral is this expression here, this divergent factor from here, and a constant that comes from doing these integrals without y1 and y2. The original integral, it is UV divergent because I'm going to come back to that in a minute. Yes, yeah. So now at this stage, you can see that this answer here is exactly what you would expect from a CFT 2-point function with that dimension. And now I can rescale the sources So the normalization of the two-point function can change if I rescale my source. I can do I can put a z factor for the source to remove this factor over here. So now to all orders, sorry, to one loop, I managed to get rid of the infinity without changing the dimension of the operator. Now the same argument actually holds to all loop. So to all loop, the computation will be something like that. So there is a blob here, which is composed out of arbitrary number of bulk-to-bulk propagators and bulk vertices. And then since that's a two-point function, eventually we have bulk-to-boundary propagators coming out. So we have a bulk-to-boundary propagator for this point to some point y1, and then another one to some point y2. It's going to be some kernel that is this black blob. And then one can do exactly the same argument that I gave you here with changing integration variables.
Self-energy could be a function of the AdS system.
This is the analog of self-energy, yes.
So it will be the function of the AdS system between these two.
Well, I mean, you will see in a moment that. Let me first finish this argument. Yes. So now you say that to all orders and non-anomalous dimensions, because I can always get rid of the infinities by just rescaling the source. Yes. Well, okay. Now, in a sense, you add an additional. Then you're asking whether the asymptotic series is convergent or not. Okay, that's an additional layer. I don't think there's any problem that has been analyzed to all orders in bulk loops. Yes, should be the same as in flat space. Yes. Yes, yes. So this argument here suggests that there are no anomalous dimensions in the CFT, or at least in a holographic CFT, but we know this is false because people have computed anomalous dimensions in a large N CFT that have a holographic dual, like for instance in N equals 4 superunion wheels. So something must be wrong in that argument. And what is wrong in that argument is that this x1 integral is indeed divergent. So you need to actually compute this integral in the presence of IR regulator. And you can do that. That's a non-trivial computation, but you can do that. And when you do that, then the integral takes now this form over here. So this is the pieces we had earlier. So first of all, there is a piece which has contact support on the y's with this dimension. Then there is a log. You have a log epsilon, and then there are some constants. And now once I have this, then the format of the divergences, of the unit divergences, are such that I cannot remove them by just rescaling the sources. I need something else. I need to introduce a mass counter term. So as I said, this diagram has been analyzed in the literature in a number of papers, 5, 10. And in all of the papers, people just automatically put this counter term if they didn't know the answer, because they knew that they wanted an anomalous dimension. And they knew that the mass, the dimension is related to the mass. So you need to do something to the mass. And they say, oh, now we put this and we remove the infinity without caring at all about what happens in the AR. Okay, the answer is not completely wrong, because clearly one does need this counter term to get the answer. But it's also not correct. And so the only reason they put it is because they knew this is what I wanted to get out of it. Okay, so yeah. Yes.
Is it a function of psi x1 x2 AdS distance?
Yeah, it is. Yes, it is a function of psi. Yes. 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 No, no, no. It's not. The only thing that you need for that argument is that everything transforms covariantly under change of variables, and the regulator propagator is invariant under AdS isometers. That's why it was important to have an AdS invariant regulator. So then whatever I will do there, because the measure is invariant, the propagator is invariant, when I do the change of variables, it will just transform according to the dimension of the object. Okay, so oops. How much time do we have? 5 minutes? 7 minutes. Yeah, so since we have 7 minutes, we're not going to discuss in detail Harry point functions. But the story goes along the same lines. So if one ignores the infrared divergences, one recovers the expected form of correlators due to conformal invariance. But now, if you have infrared divergences, this gives rise to anomalous dimensions, and this turned out to be exactly the same with what you determined by the analysis of the 2-point functions I just said. So that's a consistency check, because now you look at 4-point function, you see that you need to remove IR infinities, and you see that is going to modify, introduce an anomalous dimension. It's exactly the same anomalous dimension. Of course, it had to be the case, but also shows the consistency of the formalism. Yeah, so all of this, so I mean, I do require that things have to be absorbed. I mean, you will see also in a minute when I discuss the normalized correlators. It is highly non-trivial that all of this organize. I mean, algebraically, it's non-trivial that all of this organize. You get the same anomalous dimension in all formulas. Yes, 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 yes. Yeah, so let me skip that statement. I mean, the theory we discussed is normalizable up to d equals 6. At the beginning, d equals 6 looks mysterious, but I can explain if you ask me why it's d equals 6. Now, to actually compute requires, again, to compute new diagrams, and compute this integrals of this type. And these are computable, but I mean, again, this is new integrals. And the structure of the integrals of the answers follows from invariance under AdS isometries. Yeah, that's another lecture on its own to discuss those. Okay, normalization. So now if you choose for delta lambda and delta m to be the expressions indicated over here, all infinities can be cancelled. So I need to explain the notation. So if we have a function, let's say a naught of tau, this function will have a divergent piece, and this I will denote as div of the function. And then the piece which has a limit as tau go to 0, I would call a convergent piece, con f of tau. So here, this a naught, a1, g1, and so on are the functions that we see here. So we have e of tau, s of tau, and then there is a chi, which is given by that expression. Chi contains a and b. The epsilon dependency would come in the next slide. These functions are not, these are convergent integrals in the IR. There will be divergent integrals in the IR that would appear in the next slide. And then when you do the subtractions, there's also these red pieces, which are finite terms you can add when you do the subtraction, this parameterized scheme dependence. So this is what I call Sj earlier on, this functions f1, f2, g1. And then you can compute the renormalized mass. using these formulas. So this is going to be the m squared I had in my Lagrangian after I split. So I had m naught, which I wrote it as m squared plus delta m. I told you what delta m is. And then the normalized mass receives finite contributions for the diagrams. And this is the formula. And then from that formula, I can extract the anomalous dimension gamma by solving this formula. And now, of course, this gamma, because the normalized mass has scheme dependence, this means gamma is scheme dependent. And this is something that was missed by all previous papers. In the sense they were using one scheme or another, and then they would plot formulas for gamma, which clearly do not make sense because the answer would change if you do the subtraction in a slightly different way. So the anomalous dimension is scheme dependent, and one needs to impose renormalization conditions to fix its value. And that could be either by computing with the spectrum of strings in AdS, like we discussed earlier with flat space, or since we have the AdS-CFT, by comparing with the spectrum of the dual CFT. So we know from a CFT computation, we can compute the anomalous dimension double trace, and then we can use that information to fix part of the scheme dependence.
People ask this question, it's important that we first do this higher regulation and then first do infrared regulator first.
Yeah. So the infrared comes in the next slide. Yes, yeah. So we need to have the infrared regulation. Yes, absolutely. Okay, so infrared divergences. So this comes from integrals of this type. So you have bulk to boundary and bulk to bulk and bulk to boundary, or bulk to boundary, bulk to bulk, bulk to boundary. And to remove those requires introducing a z function for the boundary condition, which is the infrared regulator raised to minus gamma, where gamma is that expression. Yeah, exactly the same gamma. And then the boundary counterterms that you need are exactly the same boundary counterterms we had at 3 level. The only difference is that we changed the explicit delta that we had there by this normalized delta r. And then if you do this, then you can remove the infrared infinities as well, and then you can remove all your infinities, and you end up with correlators, which are normalized and finite. And which are those? In remaining -1 minute, yes? Yeah, there were 3, I think it was G1, F1, F2, G1, 3. And then there is an additional freedom to do a scaling, which I didn't put here. That's actually the four functions. So these are not fixed uniquely. You need renormalization conditions. These are fixed by renormalization conditions. Yeah, so in this case, you have to compare with the spectrum of the dual CFT. And then depending if you're looking at half DPS operator or if you're looking at the multi-trace operator, you're going to have different conditions that fixes them in different ways. So it depends really on the physics. So there's no one answer that applies to all of them. There is the normalized answer in terms of the scheme-dependent functions is unique. That's what I gave. But now to get the physics of it, you need to now say which operators you're considering. Yes, exactly. You need the analog of that. And the analog of that is to say my CFT has an operator of that dimension. Yes.
And so a related question. You can pull this self-energy to the boundary, and you can have one loop extending from boundary to boundary. So that would be the anomalous physical direction of the double trace operator.
Yeah, that looks reasonable. Yeah, that looks reasonable. It hasn't been done, I think, in this exactly in this language, but it looks reasonable. Yes. Yeah. Well, I mean, we are. Let's finish because probably they have to go. Yes, I think I only have 2 or 3 slides. Of course, with the speed we're going. So what are the results? Okay, here are the results. So for the 2-point function, the result is given by this expression, where this C of R is given by this ratio of gamma functions. So this is exactly the same expression as a 3 level. The only difference is whether you had delta, you replace by delta R. Secondly, the 2-point function, the 4-point functions are given by this formula now. So that would be the 3-level expression, where again, instead of delta R, you had delta. And now we see, first of all, we see there is an explicit scheme dependence here as well, this formula G1. And when you do the computation perturbatively, you do not get directly delta R's. You get deltas and some S that depends on lambda. And all of these factors can be, all of them are summed so that there are no explicit gammas anywhere. And all of them recombine into this delta R's. That's quite, this is the algebraically non-trivial thing I was saying earlier. Now, for this to be a 4-point function of a CFT, this means that I need to be able to rewrite it in a fashion where it makes this manifest. So it should be a function of conformal ratios, and I will discuss that tomorrow, times this function. And then one can show that this guy here can indeed be written in this fashion, where this functions of cross ratios is given by this formula over here. So 3 level would be just this term, lambda times h hat naught. The other corrections are the corrections that appear because of the loop corrections. Yeah, so that's the answer. We already over time, so let me just flash the conclusions and outlook. So I discussed with you how to set up renormalization. I think that provides further structural support for the duality. The fact that we're able to do that consistent with CFT expectations, exactly consistent with the CFT expectations without any input on the specific field, I think it's important. We carried out that program for the 5 to the 4. And of course, there's a huge amount of stuff that this still remains to be done. We only done the simplest example. Next thing would be to include graviton exchanges in the bulk. That has a number of technicalities which we are sorting out. I think it would be possible, at least in special cases, to work out all loops for general endpoint functions. And following special cases on the field theory case. And of course, I only done, and this is the left-hand side of the duality, and I started saying there's a lot of interesting work on the right-hand side from the CFT perspective. I think, again, the next step is to start now properly matching the two, because people have done a lot of good work on the CFT, but they were at most heuristic on the gravity side. So now we understand the gravity side, we should go back and really putting all of this on firmer footing. Okay, thank you.